One more problem I'll show on our blackboard here is number 47. It says we have 300 milliliters of a 0.23 molar acetic acid. HC2H3O2 is called acetic acid, and its conjugate base coming from the source of sodium acetate. They are of equal concentrations in a combined volume of 300 mils. So part A, just a straight Henderson-Hasselbalch to find the pH of our solution. pH is negative log, and again, I had to use our textbook to find the Ka value of acetic acid, 1.8, E negative 5. When the concentrations are equal, you can see that dropping off. pH is exactly pKa, 4.74 units. Letter B says, suppose we add strong acid to the conjugate pair called a buffer. If we add 0.015 moles of acid, strong acid, think about the chemistry. It's going to consume the base and make more acid. Adding acid uses base but makes more acid. So this 0.069 moles, that's just going back up here and saying 0.23 molar times the volume of 0.3 liters, molarity times liter, and it's the same for both since we had the same number provided, same volume provided for each conjugate pair, 0.069 moles. The strong acid, 0.015 moles, consumes the acetate ion, creating more acetic acid. So to this value on the left, I subtracted 0.015, and I added that to the right-hand side of our equation. The acetate went down, the acid went up. The number of moles in the new volume here, same 0.3 liters, because when I use Henderson-Hasselbalch, it has to be mole ratios over volume, so big M, molarity. I'll tell you what, if you use these values, it would still work out because we're dividing by a like number, but I'll just show the correct way, even though we can see that this would simplify. Moles over volume of the base over acid. The base got consumed, the acid got made. pH is negative log of the Ka, this is called pKa, plus the log of the new ratio of base over acid, and the pH now is 4.55. Adding acid made it go down the pH a little bit. Part C, I've got to look up, let me grab that number. 0.015 moles of sodium hydroxide. So now we're adding a strong base, 0.015 moles. That base is going to react with the acid, C2H3O2, making a conjugate of the hydroxide, water, and making more of the acetate ion. This is a base. It's going to react with our acid from the conjugate pair, creating more conjugate base. The original amount in moles, 0.069. We're going to subtract out 0.015 moles, leaving 0.054 moles divided by 0.3 liters. And again, I'm just looking at the math I did up above. This comes out to be 0.18 molar. The original number of moles, 0.069 of the conjugate base, but now I'm adding because I'm making more, stoichiometry first. So now, again, same answer up above, 0.084 divided by 0.3 liters, and we get that same concentration of 0.28 molar. pH is pKa, which I never did simplify, so I'll just rewrite it, 1.8 times 10 to the negative fifth, plus the log of the ratio of base over acid. The base has now been produced. Its value, 0.28 molar. Set over the acid, which was now 0.18 molar. So what's happened is it's exactly flipped from up above. And let's hit for the pH after adding a strong base. I suspect it's a little higher than 4.7, but not too bad. So negative log 1.8 E negative 5 plus the log of the ratio of 0.28 over 0.18, 4.94, if I round a little bit, 4.94 pH units, which makes sense. Without adding, we're at 4.74, straight pKa. Adding strong acid should make it go down a little on the pH scale. It did. And adding strong base should make it go up a little bit on the pH scale, and it did. Alrighty. Stoichiometry followed by Henderson-Hasselbalch for titration problems.